So we'll be discussing two-source interference and Young's double-slit experiment. You have pretty familiar with a situation of this type where you have two loudspeakers and you want to find out the best place to sit. People usually sit right in the middle to get optimum stereo effect. But are there any bad spots where you can sit for certain frequencies? Let's try to answer that question. Well, one way to answer that question is to figure out if the number of waves that can fit here and the number of waves that can fit over there differ in a certain way. So for example, if I have wave from L1 like that and a wave from L2 also looking like that, then you can expect that these two waves will add constructively and you'll get a wave of double the amplitude. And double the amplitude means 4 times the power, because the power of the wave is proportional to the amplitude squared. So this is a situation which you would like to have, and certainly that situation is realized being in the middle. But any other place where this is possible will also give you a loud sound. May not be the stereo effect, but you still get the same loud sound. A bad spot would be a spot where you have fully destructive interference. So this would be where the wave from one of the speakers looks like that and the wave from the other speaker looks like this. So the crests and the troughs exactly cancel out and you just get a flat line. That would be a completely destructive interference. And then of course there are gradations in between that you need to worry about. So this is really the basics of this subject of two-source interference. When the two waves are aligned, you say the path difference is either 0 or some multiple of lambda. So I'll say it's m times lambda, where m is 0, 1, 2, and so forth. Because if I displace it by an entire wavelength, it will still look like that. By the way, we are assuming that the wavelength or frequency from the two speakers are the same. So for example, you're just playing some test tone, 1000 hertz pink noise or something. Here, the path difference, they're offset by half a wavelength. So the most fundamental path difference is half a wavelength. But you can also have half a wavelength plus a whole wavelength. So here it will be m plus a half lambda for the same m's. So for example, if m equals 0, I get 1/2 lambda. If m equals 1, I get 3/2 lambda. All these look just like that. M being negative is also allowed, but I'll just stick to positive m, that is on this side. M negative would be on this side. So I'll stick to positive m, which would be on that side of the upside of the middle line. Okay, so m equals 0 would be the happiest situation where you have these two waves coming right in the middle and giving you a loud sound. The exact same experiment was done by Thomas Young, and he was the first to show that light has wave-like properties. This particular phenomenon cannot be explained without considering this waviness of the wave, as we have seen here. So in Young's double-slit experiment, you just replace these two speakers with light sources, and the distance d between the two light sources is achieved by poking two slits, and that's why it's called a double slit. DS stands for double slit. So the picture looks almost exactly the same, so I won't bother redrawing the picture for the double slit. I'll instead adapt this. We'll call this angle theta, and the path difference, the actual difference in the rays of light. These are rays of light that are the directions of the pointing vectors, and the electric field corresponding to the first one would be E1, and the electric field corresponding to the second one would be E2. So E1 of say x comma t, and E2 of x comma t would be the electric fields, and they would look something like E0 sine kx plus or minus, I'll take minus omega t with a phase factor which I'll call phi 1, and then this would be something like E naught sine of kx minus omega t plus the phase factor phi 2. Now the only purpose achieved by kx minus omega t is tracks where it is and how time moves. So the entire content of how big the wave is actually contained in these phases. So it actually makes sense to look at the whole thing in terms of just phase. So if you think of it as x equals 0 and t equals 0, then you'll just look at sine phi 1 and sine phi 2 and worry about just the phases. When you add these two waves, E1 plus E2, that's when you get the full-fledged result. Now before we do that using addition of trigonometry functions, let us take a small look at the path difference, actual path difference. What is L2 minus L1? Well, physically speaking, this right-angled triangle is what we are going to look at. So L2 minus L1 is approximately this distance, delta. Now I say approximately because I'm going to also say that this theta is the same as this theta. So if you look at this picture, I get that delta over d. If you turn your head around a little bit, delta is the opposite side and d is the hypotenuse. So delta over d is sine theta. So the path difference is actually d sine theta. So what I'll do there is I can immediately find out the conditions of complete destructiveness and complete constructiveness. Complete constructiveness is here and destructiveness is here. So let's get that criterion without any hesitation. That constructive, the path difference, which is d sine theta, must be equal to m lambda, and here d sine theta equals m plus a half lambda. So this tells me exactly where the bright fringes are going to occur for light. Bright fringes are areas which actually look like they have some light in them and they appear bright, and this is where you get the dark fringes. Now sine is not a linear function, so the dark fringes are not necessarily going to be exactly halfway between the bright fringes, although if the angle is small, they certainly will be. Now the other terms involved in Young's double slit experiment, which I should probably write here again for light. So here's the proper drawing. What you have here on the left side is some coherent source of light like laser light of wavelength lambda, and that's being incident on two slits, slit number 1 and 2, and just like you had in the loudspeaker example, the ray of light that comes from here and here will interfere at the screen. So I just wanted to draw this again because there are some geometric quantities that need to be considered. So that's d, the distance between the two slits, little d, and then here's theta, and theta is the angle subtended from the slit center point to wherever you're measuring the intensity of the light. This is typically a cardboard screen where you catch the image. So you're getting a bright fringe, dark fringe, bright fringe, dark fringe, and so on. Now, one question is where it occurs. So let's call this y, and this distance is d. So where on the screen do we find any of these patterns? Well, that can be answered through a geometrical fact, and that is y divided by d is tangent of theta, because this is also a right angle. So y over d equals tan theta, and technically speaking, you would first find sine theta and then find theta, and once you have theta, you will find tan theta, and then you will find y. That would be the proper way of doing it, and that should be your way of doing it if you're not sure the angles are small. So in reality, I would say y is equals d tan for the bright fringes. I'll say y bright equals d tan theta bright, and y dark equals d tan theta dark, where the bright and the dark parts simply come from here. So we get what we need. So when we solve for theta bright, it's arc sine of m lambda over d, and put it there, and you're all done. But there's a small angle approximation which I need to tell you about, which is used extensively in this business because d is usually very big. If d is very big, then, and this angle is really small, then we can use a small angle approximation. And let me say, this part is not important, the small angle approximation. If it's usually used in multiple choice problems, but if you have a diffraction grating, you will never use the small angle approximation. Like for example in the lab number 8, you will not be using the small angle approximation. So the small angle approximation says if theta is small, then sine theta is the same as theta is the same as tan theta. So you have this incredible fact of life. It's a very good approximation. So then I can simply write theta equals m lambda over d, and here also I can write theta, and so I get y bright equals d m lambda over d, and y dark equals d m plus a half lambda over d. So I have now I can actually show that between two bright fringes there's exactly one dark fringe halfway between. So the linearity is achieved when you remove all the non-linearity. So that's not a great surprise. Let's go back to finding out what happens in the intermediate stages. What if you have not a perfectly bright fringe or a perfectly dark fringe, but some in-between gray area? How does that how is that analyzed? That's analyzed by simply adding two trigonometric functions. So if you have E naught, let's call this sine of alpha, and this is sine of beta. So you're going to get sine of alpha plus sine of beta. So you've got to add a sine of something and a sine of something else. Now one way to do that is to expand alpha as kx minus omega t plus phi 1 and beta as kx minus omega t plus phi 2. Play the usual mathematical rules of trigonometry and you'll get the answer. So I'll play it slightly differently. I'll do the following. Let me first recall what sine of a plus b is. Sine of a plus b is sine a cosine b plus cosine a sine b. If you've not learned it, well, you know it now. Similarly, sine of a minus b. Now if I had taken cosine for these two, I would use cosine. I just happen to take sine instead of cosine. And that would be sine a cosine b minus cosine a sine b. Now here I have a sine alpha and a sine beta. I'm going to add. So I'm going to add these. So I'll get sine of, and I'm also going to call a plus b alpha, and I'm going to call a minus b beta. So I get sine alpha plus sine beta. So that's sure enough what I need. And that gives me, these two terms will cancel out, and so I can get 2 sine a cosine b. Meanwhile, if alpha is equal to a plus b and beta equals a minus b, then I know that a equals, if I add them both, I'll get alpha plus beta divided by 2, and b would be alpha minus beta divided by 2. Once you've done all these basic mathematical steps, your answer just pops right out. So this is just 2 times sine of alpha plus beta divided by 2 cosine alpha minus beta divided by 2. Done. So with that intermediate result, let's proceed to add the two electric fields. The two electric field additions, E total, is going to be E1 plus E2. Let's call this E total. And it's E naught times all this, 2 times sine alpha plus beta over 2. If I do alpha plus beta over 2, that I'll still get kx minus omega t. And then I'll get the average of the two faces. So I'll call that phi bar. And then cosine, this is where the money is. Alpha minus beta, when I do the minus, the kx minus omega t will cancel out, leaving us with just the phase difference, phi 1 minus phi 2 divided by 2. The intensity is defined as the average of the electric field squared. When you take the average, what happens is that this part just gives you it just disappears, and then you just get 2 times E naught, that gives you 4 I naught, 4 E naught squared, let's say. There's also some other constants, so I'll just put a proportionality sign. Cosine squared, phi 1 minus phi 2 over 2. And then, lastly, I'm going to relate the phase difference to a path difference. And the phase difference, delta phi over 2, is going to be 2 pi by lambda times the path difference, delta. So once I have that, this problem is completely solved.